Welcome, everyone. I'm excited to kick off our presentation today. Our first slide is titled, Understanding the Physical World. Today, we'll explore how we perceive and interact with the physical universe around us. We'll cover key concepts that help us make sense of the natural phenomena we observe daily. Let's dive in and discover what makes the physical world so fascinating. Let's take a closer look at some of the key concepts we'll explore today. First, the enormous strength of electromagnetic fields, or EMF, is truly remarkable and plays a vital role in many technological advances. Moving on, we'll examine the universal gravitation equation, which helps us understand the gravitational forces that govern planetary movements and objects in space. We'll also look at the various contributions scientists have made over time, shaping our understanding of these forces. The scientific method itself is fundamental. It's how we systematically investigate and uncover the laws of nature. Next, we'll discuss the nature of EMF, what it actually is, and how it interacts with matter. The gravitational force, another fundamental force, is what keeps planets in orbit and influences everything on a cosmic scale. Physics, as a broad field, seeks to explain the fundamental principles that underpin our universe. So, what exactly is science? It's a methodical way of understanding the natural world through observation, experiment, and reasoning. We'll also touch on the electromagnetic force, which is responsible for electricity and magnetism, and the inverse square law, describing how these forces diminish with distance. Forces are the interactions that cause objects to accelerate or change motion, and models are simplified representations that help us grasp complex phenomena. The word science itself embodies our quest for knowledge, linking everything together. Furthermore, we'll see how science connects to technology, how our scientific discoveries lead to practical innovations. Lastly, we acknowledge that changes in our understanding or the environment are always permanent. Once we learn something new, it transforms our perspective forever. All of these points come together to give us a comprehensive picture of the physical world and our ongoing pursuit to understand it better. Humans have always been curious about the world around them. From the earliest times, we looked up at the night sky and marveled at its bright celestial objects. This fascination has driven us to observe our environment very carefully. We looked for meaningful patterns and relationships in natural phenomena, trying to make sense of everything we saw. Over time, this curiosity led us to develop new tools and methods to interact more effectively with nature. This human drive to understand the world is what eventually gave rise to modern science and technology. So when we ask, what is physics? We're really asking about the fundamental study of these natural patterns and the laws that govern the universe. It's the branch of science that seeks to understand how everything works, from the tiniest particles to the vast cosmos. And this pursuit connects directly to the broader theme of how humans have always tried to comprehend and harness the natural world around us. Veynan and the Arabic word ilm convey similar meanings, both referring to knowledge and understanding. It's interesting to see how these terms from different languages and cultures highlight the universal pursuit of knowledge. Now, moving to the Sanskrit word for science, which is also deeply rooted in the idea of knowing and understanding. Science, in a broad sense, is as old as humanity itself. From the earliest civilizations, Egypt, India, China, Greece, Mesopotamia, people have made vital contributions to our collective progress. These ancient cultures laid the foundations for scientific thought and discovery. And if we look at the Latin origin of the word science, which is scientia, it means to know. This highlights a fundamental aspect of science, the pursuit of knowledge. So whether we call it ilm, veynan, or scientia, the core idea remains the same. It's about understanding the world around us. This connection across languages and cultures emphasizes that the quest for knowledge is a shared human endeavor, integral to our progress and development. Science is a systematic attempt to understand natural phenomena in as much detail and depth as possible. It's about using the knowledge we gain to predict, modify, and control the phenomena around us. Essentially, science involves exploring, experimenting, and making predictions based on what we observe in our environment. The curiosity to learn about the world and to unravel the secrets of nature is really the first step toward discovering science. This curiosity drives us to ask questions, to seek answers, and ultimately to deepen our understanding of the universe. So, in a way, science is our organized effort to make sense of what we see and experience every day. So, when we talk about the scientific method, one of the key aspects is the ability to verify or falsify theories. This means that through careful testing, we can confirm if a theory holds up or if it needs to be revised. Prediction is another crucial component, using what we know to forecast future observations or results. Mathematical modeling helps us create precise representations of real-world phenomena, making complex systems more understandable. We also rely on both qualitative and quantitative reasoning. Qualitative reasoning helps us understand the nature or characteristics of something, while quantitative reasoning involves numerical data and measurements. Controlled experiments are essential because they allow us to test variables systematically, minimizing outside influences. And of course, systematic observations provide the reliable data we need to support our hypotheses. All these steps are interconnected, forming a comprehensive approach to scientific investigation. They work together to ensure our findings are thorough, accurate, and reliable, ultimately advancing our understanding of the world around us. Now, let's look at Johannes Kepler, who lived from 1571 to 1630. Kepler built on the data collected by Tycho Brahe, who was active from 1546 to 1601. Brahe's meticulous observations provided the crucial details needed for understanding planetary motion. Before Kepler's work, the common belief, influenced by Nicolaus Copernicus, was that planets moved in perfect circles around the sun, which is the heliocentric model. However, when Kepler analyzed the data, he realized that the planetary orbits couldn't be accurately described as circles. Instead, they had to be elliptical, that is, oval-shaped to match the observations better. This was a significant shift because the existing theory, which assumed circular orbits, simply couldn't explain the new data. It's a perfect example of how scientific understanding evolves. Our models must adapt when new evidence emerges. Moving forward to the early 20th century, scientists faced similar challenges. Even Newtonian mechanics, which had been incredibly successful in explaining a wide range of phenomena, struggled to account for some atomic-level behaviors. This highlights a key theme. Changes in scientific theories are often permanent. They reflect our growing understanding and are essential for progress. So, throughout history, we see that scientific knowledge is not static. It's constantly refining itself in response to new data and insights. Let's look at some key milestones in the development of atomic models. In 1911, Ernest Rutherford conducted his famous experiment where he scattered alpha particles off gold foil. This experiment was groundbreaking because it led him to propose the nuclear model of the atom. Essentially, he showed that an atom has a tiny, dense nucleus at its center, with electrons orbiting around it. This was a huge leap forward from earlier models. Building on Rutherford's work, in 1913, Niels Bohr introduced the quantum theory of the hydrogen atom. He proposed that electrons orbit the nucleus in specific, quantized energy levels. This model explained spectral lines and earned a lot of support for the idea that energy levels are discrete. Meanwhile, on a different front, the concept of antiparticles was first introduced theoretically by Paul Dirac in 1930. His equations suggested that every particle has a corresponding antiparticle with the same mass but opposite charge. This was a fascinating idea, but it wasn't just theory. 2 years later, in 1932, Carl Anderson experimentally discovered the positron, which is the antiparticle of the electron. This discovery confirmed Dirac's predictions and opened up a whole new chapter in particle physics, helping us understand matter and antimatter much better. All these models and discoveries are interconnected. They've shaped our modern understanding of atomic and subatomic structures. Physics is a fundamental discipline within the category of natural sciences. The word physics actually comes from a Greek word that means nature. which highlights its focus on understanding the natural world around us. Interestingly, in Sanskrit, the equivalent term is bodhiki, which is also used to refer to the study of the physical universe. This connection between languages shows how the quest to understand nature is universal across different cultures. As we explore the broader theme of scientific inquiry, physics serves as the foundation for understanding the laws and principles that govern everything from the smallest particles to the vast cosmos. Let's take a moment to explore the contributions section. Here, I want to highlight the key points that have emerged from our work. First, the major contributions include developing innovative methods that enhance efficiency and accuracy. These advancements are crucial because they directly support the overall goal of improving our processes. Additionally, we've identified new insights that can inform future research and practical applications. By connecting these contributions back to the overarching theme, it's clear how each piece fits into a larger picture of progress and innovation. Ultimately, these contributions demonstrate our commitment to pushing the boundaries and making a meaningful impact in this field. Let's explore the fascinating link between technology and physics. As we've seen, physics provides the fundamental principles that underpin many of the technological advancements we use today. For example, understanding electromagnetism has led to the development of everything from electric motors to wireless communication. Similarly, quantum physics has paved the way for innovations like quantum computing and highly secure data encryption. This connection is crucial because it shows how deep scientific understanding directly fuels technological progress. Throughout this presentation, we've been emphasizing how science and technology are interconnected, and this slide highlights that relationship vividly. Recognizing this link helps us appreciate how advances in physics can lead to transformative technologies that shape our everyday lives. Let's take a closer look at some of the different types of forces that influence the world around us. First, we have the electric force, which is the force between electric charges. It's responsible for many phenomena, from static electricity to how particles interact at the atomic level. Next is the buoyant force, which is what makes objects feel lighter when they're submerged in a fluid like water. Think of how a boat floats. Muscular force is generated by our muscles when we move or lift objects, highlighting how vital our body's own forces are. Magnetic force, on the other hand, is the force exerted by magnets, which is essential in many modern technologies. Tension is the force transmitted through a string or a cable when it's pulled, such as in a tug-of-war or a suspension bridge. Then there's viscous force, which acts against objects moving through a fluid, like air or water. This is what creates drag on a moving car or swimmer. Gravitational force is perhaps the most familiar. It's the force that pulls objects toward the Earth and keeps planets orbiting the Sun. Friction is the force that opposes motion between two surfaces in contact, which we experience every day when walking or driving. All these forces are governed by Newton's laws of motion, which provide the foundation for understanding how objects move and interact. When we talk about forces in general, they are the push or pull that cause changes in motion or shape. Recognizing these different types helps us understand the complex interactions that shape our physical world. The gravitational force is essentially the force of mutual attraction that exists between any two objects because of their masses. It's a universal force, meaning it applies everywhere in the universe. Every object, no matter how big or small, experiences this force due to every other object around it. For example, all objects on the Earth feel the force of gravity from the Earth itself. Now, the gravitational force is always attractive. It always pulls objects toward each other, never pushes them apart. This means that every object, including you, is pulling on every other object in the universe. It's a constant, invisible force that acts between all masses. This idea is captured beautifully in Newton's universal law of gravitation, which states that every mass attracts every other mass with a force that's proportional to their masses and inversely proportional to the square of the distance between them. So, in essence, gravity is the universal glue that keeps planets in orbit, keeps us anchored to the ground, and governs the motion of everything in the cosmos. So, If you know how massive two objects are and how far apart they are, you can actually figure out the force between them. The key variables here are r, which is the distance between the objects measured in meters. Then there's m, representing the mass of one of the objects, measured in kilograms. G is the gravitational constant of the universe, and it's always the same number. This is what makes the force calculation universal and consistent. M is the mass of the other object, also in kilograms. F is the force of gravity between these two objects, and it's measured in newtons. All of these come together in a very important equation, called the universal gravitation equation. This equation describes the force between any two objects out there in the universe, no matter what they are. It's a fundamental concept because it helps us understand how objects attract each other through gravity, whether it's planets, stars, or even galaxies. So, understanding this equation is crucial because it connects the mass of objects and their distance to the gravitational force they exert on each other. Let's talk about how the gravitational force changes when the distance between two objects varies. This can be really useful for making rough comparisons between different situations. For example, if you have the distance between two objects, the force between them actually increases by a factor of 4. That might seem a bit counterintuitive at first, but it makes sense when you think about the inverse square law. Now, if you triple the distance, the force drops to just 1/9 of what it was. And if you double the distance, the force is reduced to 1/4 of the original force. This shows that the force doesn't just decrease linearly with distance, but rather according to this special relationship. Because of this relationship, we call it an inverse square law. You can see that in the equation, the distance, or r, is squared at the bottom. So overall, this inverse square law explains how the gravitational force weakens rapidly as objects get farther apart. Electromagnetic force is the force that acts between charged particles. When these charges are at rest, the force between them can be described quite simply by Coulomb's law. This law tells us that unlike charges, like positive and negative, attract each other, while like charges, such as two positives or two negatives, repel each other. But things get more interesting when charges are in motion. Moving charges generate magnetic effects, which means they create magnetic fields around themselves. And these magnetic fields, in turn, exert forces on other moving charges. So, electric and magnetic effects are deeply connected, actually inseparable in many situations. That's why we refer to this combined interaction as the electromagnetic force. In essence, what we're seeing is a unified force that governs a wide range of phenomena, from the tiny interactions between particles to the vast electromagnetic waves that travel through space. Understanding this interconnectedness helps us grasp the fundamental nature of how the universe operates on both small and large scales. The gravitational force and electromagnetic force both act over large distances, and what's interesting is they don't require any intervening medium to exert their effects. Among these two, the electromagnetic force is enormously stronger than gravity. For example, the electric force between two protons is about 10 to the power of 36 times stronger than the gravitational force between them at the same distance. This huge difference in strength means that at atomic and molecular scales, the electromagnetic force completely dominates. It's the key player in shaping the structure of atoms and molecules, driving chemical reactions, and influencing the mechanical, thermal, and other properties of materials we encounter every day. In fact, many of the macroscopic forces we're familiar with, like tension, friction, the normal force, and spring forces, are all rooted in electromagnetic interactions. So, understanding this force helps us grasp a wide range of phenomena, from the tiniest particles to large-scale physical forces. Gravity is always attractive, meaning it pulls objects toward each other, regardless of what they are. In contrast, the electromagnetic force can be either attractive or repulsive, depending on the charges involved. Most matter around us is electrically neutral, which means it has a net charge of 0. Because of this neutrality, the electric forces tend to cancel out on large scales, so gravity generally dominates terrestrial phenomena. However, electric forces become very significant in specific contexts, like in the atmosphere, where atoms can become ionized. This ionization leads to the buildup of electric charge and ultimately results in phenomena such as lightning. Now, when we think about the strength of the electromagnetic force, it's truly enormous compared to gravity. This tremendous strength explains many energetic phenomena in nature and technology. Understanding this contrast helps us grasp why gravity governs large-scale structures like planets and galaxies, but electromagnetic forces are key to many processes at smaller scales. So, in essence, while gravity is the dominant force on a cosmic scale, the electromagnetic force's immense strength makes it crucial for many dynamic and energetic events in our daily environment.